Hello. We've been talking about using trigonometry to solve right triangles. And today we're going to talk about using some trigonometry to solve triangles that are not right triangles. They call them oblique triangles. So the two rules we're going to learn today are called the law of sines and the law of cosines. So let's start out with the law of sines. You remember back to geometry, there were certain combinations of sides and angles that if you knew they were congruent in two triangles, then you could prove that the two triangles were congruent. So we named those using letters ASA, AAS, and so on. Certain combinations of sides can let you use certain types of equations to solve the triangle. So the law of sines, remember, when we label a triangle, we use capital letters to label its vertices, and the mathematical tradition is that we call the opposite side the lowercase of the side of the letter we use to name its angle. So the law of sine says that in any triangle, the length of the opposite side over the sine of its angle is a constant ratio. So A over sine of A is equal to B over sine of B is equal to C over sine of C. Or you could take the reciprocals of all three and put the sines on the top and the lengths on the bottom. This equation can be used to solve a triangle when you know three of its parts. And remember, solving the triangle means finding all the missing parts. But you have to have at least one of these three fractions complete by replacing it with the known parts. So that means we need at least one angle with its opposite side and then one other piece in order to find the answer for all the other missing pieces. So ASA, AAS, and ASS, which I put in that order on purpose because remember, when you learned about congruence of triangles, ASS did not prove two triangles are congruent. And the reason it doesn't is because there can actually be one, two, or no solutions to make a triangle congruent, even though an angle and the two sides that are not forming it can be congruent, or it might not be congruent. You might have two different triangles, or there might not be a triangle at all. So that's called the ambiguous case. So we're going to skip over the law of cosines for a moment and just look at the law of sines. Okay, so here's an example of a problem where we want to use the law of sines to solve it. Notice that we have two angles and the included side. Well, you might be thinking, wait, didn't she just say we had to have at least one angle with its opposite side? Well, remember, when you know two angles of a triangle, since you know the angles add up to 180 degrees, you can always find the third angle. So we could use the law of sines to solve this, and that's what we're going to do. So first of all, I need to find that missing angle. So the measure of angle B is going to be 180 degrees minus the sum of the 49 degrees and the 102.3 degrees. So that's 180 minus 151.3. And that makes it 28.7 degrees. So that's one of the three missing parts that we've already found. Now, we still need to find side A and side C. Well, this law of sine says A over the sine of A, and the sine of angle A is 49 degrees, so the sine of 49 degrees, equals B, which was 27.4, over the sine of angle B, which we just found was 28.7 degrees, equals C, which we don't know, over the sine of C, and the angle C is the 102.3 degrees. So this is a three-part equation. We can only deal with two parts at a time. So I need to use the complete part, the part that has all numbers plugged into it, and either one of the two parts. So I'll use the A part first. So we have two fractions equal to each other. In order to get a by itself, we would have to multiply both sides of this by the sine of 49 degrees. So that would give us a equals 27.4 times the sine of 49 degrees divided by the sine of 28.7 degrees. Now that it's all solved for a, we can just put that into the calculator. Just going to move it over so I can see the equation here. 27.4 times the sine of 49 degrees, and actually before I finish this I'm going to hit mode to make sure. No, see, I was set in radians. I know it's a little blurry for you guys, but I need to make sure it's set in degrees because we are working in degrees. Okay, so 27.4 times the sine of 49 degrees divided by the sine of 28.7 degrees. And that comes out to 43.061 rounded to 3 decimal places. Now that I've found side A, I need to find side C. So now I'm going to use the complete fraction. I don't want to use the one I just found because I rounded that off. I want to use the one I was given with the fraction that has C in it. So taking this equation, if I want to get C by itself, I would multiply both sides by the sine of 102.3 degrees. So that would give me 27.4 times the sine of 102.3 degrees divided by the sine of 28.7 degrees. And that's going to give me C. So again, (27.4) times the sine of 102.3 degrees divided by the sine of 28.7 degrees is 55.747, rounded to 3 decimal places. So the 3 missing parts of this triangle were angle B was 28.7 degrees, side A was 43.061, and side C was 55.747. Since we weren't given any units in the original problem for the lengths, we don't have to label these. But if the original problem had units, then we should label the answers with units. Looking at another example, notice in this case we are given an angle and its opposite side. This case we have an angle, a side, and a side. So this is that ASS scenario, which means we might have no solutions, or 1 solution, or 2 solutions. So we need to be careful when we're solving this. We only know one angle, so I'm going to set up the problem. So the 22 is like our little a because it's opposite angle A. The 12 is our little b because it's opposite angle B, and the missing side here is C. We cannot use the Pythagorean theorem on this because it's not a right triangle, or at least we don't know that it's a right triangle. So if we set up the law of sines, we get 22 over the sine of 42 degrees equals 12 over the sine of angle B equals little c over the sine of angle C. So when we look at this 3-part equation, this part is complete with all numbers plugged in. This part is only missing one thing, so that means we can solve this equation. Notice that the third fraction has 2 missing items, side C and angle C. So we can't solve this until we've found one of them. So the first thing we need to find is what angle B is. So in this case, if we're trying to get B by itself, the first thing we need to do is get sine of B out of the denominator. So I'm going to multiply both sides by, actually, I'm going to cross multiply because people usually find that a little easier to see. So that gives me 22 times the sine of B equals 12 times the sine of 42 degrees. Then I want to get the sine of B by itself before I can get B by itself. So I'm going to divide both sides by 22. So now I have the sine of B is this expression. Well, to undo sine, we need to use the arc sine or the inverse sine. So we take the inverse sine of the sine of B equals the inverse sine of this whole expression. So on this side, the inverse sine and the sine cancel, leaving angle B. And we need to find the arc sine or the inverse sine of that fraction. So here again, bad reflection, sorry about that. Inverse sine is second sine, and I'm going to use my fraction template, alpha y equals 1. Oops, wrong button there. Alpha y equals 1. There we go. 12 sine of 42, close the parentheses, over 22. And that gives me 21.406, blah, 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 blah. So 21.406. And this is an angle, so that's in degrees. Now, I don't like to use rounded off things if I can avoid it, but in this case, I can't avoid it. Because in order to find angle C, I have to do 180 minus the 42 plus the 21.406. So instead of using the rounded value, I'm going to store that value. I'm going to store it into B since it is angle B. And then I'm going to do 180 minus angle B plus the 42 degrees. And that gives me 116.594. I'm going to store that into C. So again, when I need to use it later, I'm using a non-rounded version. So I did 180 minus B plus 42, and that gave me 116.594 degrees for angle C. So now that I know angle C, I can go back up to my equation, and again, I want to avoid using the rounded answer, so I'm going to connect it with this one to try to find the missing side. So now I have 22 over the sine of 42 degrees equals little c over the sine of angle C. And I'm just going to leave it C here because I'm going to use the stored value in the calculator to find it. But I'm just going to solve this to get little c by itself. So to do that, I'd have to multiply both sides by the sine of C. So that gives me 22 times the sine of C over the sine of 42 degrees equals little c. And now I'm going to put that into the calculator. So I'm going to use my fraction template. 22 times the sine of alpha C, close parentheses, over the sine of 42, close parentheses. And I get 29.400 to 3 decimal places. So to solve this triangle, I found that the measure of angle B was 21.406 degrees. The measure of angle C was 116.594 degrees. And little c was 29.400. And again, they didn't give us units here. Now, there's one thing that I didn't quite pay attention to when I did this. This is why this is the ambiguous case. And we haven't learned about this yet, but when you do the inverse sine of an angle, we haven't talked about sines that are for angles that are over 180 degrees yet. Or sorry, over 90 degrees. The sine of an angle in the first quadrant is equal to 180, the sine of the angle that's 180 minus that angle in the second quadrant. So when we get this answer for B, B could also be 180 minus 21.406 degrees. So 180 minus 21.406 degrees, actually I'm just going to put 180 minus B, is 158.594. And when we get that angle, if we went to try to find angle C, then C would be 180 minus B, which I'm actually going to store into E since we already used B, the quantity E plus 42. Well, if you take that 158, so first I'm going to store that 158 angle into E. I like E because it's right below B, so that reminds me it's an answer for B. And then I'm going to do 180 minus angle E plus 42. Notice that it gives me a negative answer, which means angle C would have to be negative. And it can't be a negative angle if it's in a triangle. So that means this second answer for B actually does not give us a solution for the triangle. So this was one of the ambiguous cases where there was exactly one solution. When you get to that arc sine part, you always have to check for the angle that you get by just putting it into the calculator, and then the angle you get by doing 180 minus that angle for that angle. And then you need to check to see if angle C exists or not. So you'll get one answer, and then maybe you'll get another answer, but if you can't get a positive angle for angle C, then that answer goes away, and you only get one solution. Sometimes when you put in your arc sine here, you're going to get an error message, and that means there's no such triangle that has the dimensions that they gave you to begin with, so there would be no solution. Okay, one more example for the law of sines. This time they didn't draw you a picture, so you might find it helpful to draw yourself a picture. But remember, the angle and the side opposite it have the same letter name, just lower and uppercase. So in this case, A over sine of A would be 12 over 20.5. B is 31 over the sine of B equals C over the sine of C. So this is like the last one we just did. We're trying to solve the triangle. So first we have to look at the fraction that has numbers plugged in for everything and the fraction that's only missing one thing. So we're looking at this equation first. So since the sine of b is in the denominator, we're going to cross multiply. That gives us 12 times the sine of b equals 31 times the sine of 20.5. And then to get sine of b by itself, we divide by 12. So we get the sine of b equals 31 sine of 20.5 degrees over 12. So I'm going to put that into the calculator. Oh, sorry. No, I'm not going to put it in the calculator yet because I need to do the arc sine of both sides. So if I take the arc sine of the sine of b, that's going to cancel. And over here I'm going to have the arc sine of 31 sine of 20.5 over 12. So, arc sine of the fraction 31 sine of 20.5 over 12. Whoops. And I get angle B is 64.783. But remember, I'm going to store that into B. I also need to consider the angle 180 minus that. So 180 minus that answer gives us 115.217. And I'm going to store that one into E. So I have two different answers that I could use for angle B. So I stored this one into E, I stored this one into B. So now angle C is going to be 180 minus the 20.5 that they gave you plus the angle B. So 180 minus the quantity 20.5 plus alpha B is 94.717. Or, now I have to do it with the other angle, the 115. So 180 minus the quantity 20.5 plus angle that I stored in E is 44.283. So this time I got two different answers for C, which means this problem is going to have two solutions. So you need to make sure you keep the solutions that went together together. So far I have the measure of angle B is 64.783. The measure of angle C that went along with that one is 94.717. And my second solution has angle B as 115.217 degrees, and it has its angle C as 44.283 degrees. So now I have to solve the C equation twice. One using this measure of angle B and the other using this measure of angle B, or whichever. So, or sorry, C in this case. So going back down here, again I'm going to use the complete fraction with the one I'm trying to solve. So I have 12 over the sine of 20.5 equals C over the sine of C. And again, I'm going to make sure that I stored my answers for C into C for the first one and into F for the second one. So my answer for the first C was the 94. So I'm going to store that into C. And then the second one was the 44. And I'm going to store that into E, or F rather. So to get little c, because I know angle C now, I just need to multiply both sides by the sine of C. So I get 12 times the sine of C over the sine of 20.5 equals little c. So 12 sine of alpha c, close parentheses, divided by the sine of 20.5 is 34.149. So that would be the solution that goes with my first solution, 34.149. And then I also need to solve 12 sine of, remember I stored the second solution into f over the sine of 20.5. So 12 sine of alpha f, close parentheses, divided by the sine of 20.5 is 23.924. So my two solutions, I have one triangle where you're given little a, little b, and angle A. The other missing sides would be angle B would be 64.783 degrees, angle C would be 94.717 degrees, and side C would be 34.149 degrees. You have a second solution where angle B would be 115.217 degrees, angle C would be 44.283 degrees, and angle C would be 23.924. I'm going to do a separate video for the law of cosines.